Hello YouTubers. Today we are going to discuss here the angular displacement, angular velocity and angular acceleration. Likewise, the linear quantities, that is linear displacement, linear velocity and linear acceleration, they are the angular quantities derived for the circular motion. So first we see the derived angular quantities, that is angular displacement, angular velocity and angular acceleration for the circular motion. So first we see the angular displacement. So first consider the circle having radius r. Also consider the radius vector OA, and the initial position of the radius vector is considered as A, and the final position of the radius vector is considered as a B. So this radius vector is moving along the circumference of the circle, making an angle theta at the center of the circle, and cuts the arc is considered as a S. So this theta is actually your angular displacement, and it is defined as, and it is basically defined as the angle made by the radius vector at the center of the circle with respect to time is called as angular displacement. So angular displacement is given by theta, where theta is equals to arc length upon radius. So here arc length is considered as a S and radius is considered as a r. So this equation becomes theta is equals to S upon r. So this is the required condition, or this is the required equation for the angular displacement, and its unit is radian. This equation can also be written as S is equals to r theta. I have written this equation in the side because we are going to use this equation afterwards. So we are going to write this as equation 1. From the angular displacement, we are going to derive the angular velocity. And angular velocity is defined as the rate of change of angular displacement, that is del theta, with respect to time, that is del t, with short time. So here I am going to write limit del t tends to 0, and angular velocity is given by omega. So angular velocity is defined as the rate of change of angular displacement with respect to time, and the condition is the time limit should be very small, and it is denoted by omega. So omega is equals to limit del t tends to 0 del theta upon del t, and the unit for the angular velocity is radian per second. Likewise, the angular velocity, we can derive the angular acceleration, and angular acceleration is defined as the rate of change of angular velocity with respect to time, and here again the condition is time limit should be very small. So rate of change of angular velocity with respect to time is known as angular acceleration, and the condition is time limit should be very small. And the unit for the angular acceleration is radian per second square. So these three are the most basic and important quantities for the circular motion, or the particle which is performing for the circular motion. From this derivations or from this formula, you can calculate the angular displacement, angular velocity or angular acceleration by given data or given conditions. So what about the direction of these three quantities when the particle is performing the circular motion? Actually, it is given by the right hand screw rule. It says that if you held the axis of rotation in the right hand, so this curved finger gives the direction of the motion of the particle, and this outstretched thumb gives the direction of angular displacement, angular velocity and angular acceleration. So now the remaining is the relation between the linear velocity and the angular velocity. For this, consider a particle, consider a particle which is performing a circular motion, and this circle is considered as the path of the particle moving in a circle or performing a circular motion, and the initial position of the particle is A and the final position of this particle is B. So what about the linear velocity of the particle? What about the angular velocity of the particle? So this particle is making an angle theta, means here the angular velocity, angular displacement is included, angular velocity is included, and angular acceleration is also included if the angular velocity is changing. So for deriving the relation between the linear velocity and the angular velocity, we are using this equation S is equals to r theta. Now we are going to differentiate it partially with respect to time and keeping limit del t tends to 0. Therefore limit del t tends to 0, del s upon del t is equals to, here the radius of the circle is constant. So kept it as a constant and limit del t tends to 0, del theta upon del t. Actually, the definition for the linear velocity is the rate of change of linear displacement with respect to time is known as linear velocity. And here S is the linear velocity, linear displacement, because the radius vector is moving along the circumference of the circle, making arc S, and this arc S is straight line if the time limit should be very, very small. If the time limit is very, very small. So this quantity becomes V, that is linear velocity. This R remains constant, that is R, and this quantity we have derived initially, that is the rate of change of angular displacement with respect to time, means angular velocity, that is omega. So this is the required relation between the linear velocity and the angular velocity. If you want to convert it in the vector form, you can directly write it as V bar is equals to omega bar cross R bar. So this is the required vector relation between the linear velocity and the angular velocity. So I think this is the efficient video. For you to understand the concept, what is the angular displacement, angular velocity and angular acceleration, and the relation between the linear velocity and the angular velocity. So if you watch it thoroughly, you can remember it and write it, and you can use use the application of this in the CET exam. Thanks for watching.